Hi there, I'm Safia, and welcome to my GOTO Chicago talk. This talk is going to give you all the insights you need to know about the Git version control system. A couple of things before the talk starts. First, I'd like to introduce myself. As you know, my name is Safia. I'm an open source maintainer and contributor and a software engineer at Microsoft. I live and breathe on Git, so I figured it's perfect for me to make a talk about it. About the talk itself. This talk is designed to be interactive. We're going to be spending most of our time on the command line. So if you're on a machine with Git installed and access to a command line interface, you can follow along with this talk. The exact values and outputs that you see might not be the same, but the general principles will still apply. If you don't have access to Git or a command line interface, no worries, you can still follow along with the screenshots in the presentation. As we go along the talk, feel free to post questions that you have within the Zoom chat. At the end of the talk, I'll go through all the questions and answer them. With all that in mind, let's get on with the talk, and I'll see you at the end. If you work as a software engineer in a team, you're probably familiar with a piece of software called Git. It's probably a part of your development workflow. You type a few magical incantations and somehow your code ends up on a centralized server somewhere for your teammates to review. Occasionally, something goes wrong and you type a few more commands, and if you're lucky, things sort themselves out. My goal in this talk is to help you get Git. Try saying that 5 times fast. To understand what is going on under the hood as you execute a variety of common commands in your Git workflow. But before we go under the hood, we have to travel to the past and learn a little bit about the history of version control systems. This history isn't going to cover every tool, just the ones that I think are indicative of the technological changes in version control systems. We'll start by traveling all the way to Bell Labs in 1972, and the dawn of one of the first version control systems, source code control system. The architecture of the tool consisted of 3 different parts: a delta table, control and tracking flags, and a set of control records. The delta table, as you might expect, is a table that stores each of the changes made to a file. Control and tracking flags were used to set permissions and control releases. And control records were used to keep track of when lines of code were deleted or inserted into a file by storing those insertions and deletions into special records. In this way, this version control system pioneered some of the early principles that we'll come to see in later version control systems. SCCS, as it was known, was popular until the year 1982, when its successor, Revision Control System, came to prominence. The RCS system was not distributed at all, so it wasn't possible to store copies of the code that you were versioning on a central server or another machine. Multiple people couldn't edit the same file at the same time, so merge conflicts weren't really a thing that happened. It had one simple job: store different versions of code. Next, we'll travel to 1990 and the release of the concurrent version system, commonly known as CVS. Unlike RCS, CVS employed a client-server model. A copy of the repository was stored on a central server, and several clients could make copies of it. At this point in time, it was possible for multiple people to be editing the same file, so it was possible for 2 individuals to make conflicting changes. To work around this issue, CVS required that you fetch and merge the latest changes from the server into your code before making any commits. Finally, we'll travel a little over a decade ago to the year 2005, where a tool that we're all familiar with came to fruition: Git. Git was different from its predecessors in a lot of ways. For one, it didn't require you to be on the latest version of a file before making changes. You could make a change to a file and then pull in any updates that happened after you made the change. Furthermore, Git was distributed in a decentralized nature. Git repositories could exist in a first-class nature on developers' machines, GitHub servers, your company's CI build, and so on. Why did Git get so popular? It was for a couple of reasons, and everyone has a perspective on what those reasons were. Tools like GitHub certainly made Git a little more popular by providing a centralized space for developers to discover and share code, adding a social aspect to an otherwise unsocial tool. Git also had a merge strategy that was a lot easier to navigate than its predecessors. And finally, after development, Git was used as the version control system for the Linux kernel codebase, giving it an immediate large early adopter. People's opinions on the reasons for Git's rapid adoption differ, but in any case, here we are. Most software teams use Git to version control and collaborate on their code bases.
So how do most people use Git? Well, at your first day of work or university, you probably ran a command like this to get the latest copy of a code base from a remote server onto your machine. Go ahead and try it now. What did this command just do? There's all this business about objects and deltas and compressing and enumerating and resolving, and oh my goodness, there's quite a lot going on in such a few lines of standard output. To dive a little bit more into this, we're going to need to poke into a directory that exists on every Git versioned project, the .git directory. Here's what its contents look like in our newly cloned repo. There's an objects directory in there. I wonder if that can give us a clue on the objects that we saw in the standard output of our git clone command earlier. Let's poke around and see if we can get a sense of what Git might have been enumerating and counting and compressing when we cloned our directory. There's only two directories in there, info and pack. Let's dive into them and see what we can find out. Now we're getting somewhere a little bit more interesting. The info directory is empty, but the pack directory contains two files, one with an IDX extension and another with a .pack extension. We'll focus on the file with the .pack extension for now. Now, we could try to cat these files to look into their contents, but they're binary files, so looking at the output won't be too much help. Give it a try right now and see. You can see from the output above that the pack file contains about 50,000 objects. The word pack is starting to take on a different meaning now. Perhaps the pack is a collection of those Git objects, packed together in some optimal fashion. I'll stop beating around the bush now and provide a quick refresher on what Git objects are. Objects in the Git context consist of a type, a size, and some contents. There are four types of objects. Blobs, objects that are used to store file data. Trees, objects that are used to reference multiple blobs or other tree objects, kind of like a directory. Commits, objects that contain references to a particular tree, the timestamp on which a commit was made, the creator of the commit, and other metadata. And finally, tags. Annotated tags are stored as objects in Git. Similar to commits, they contain a timestamp, an author, and an associated message. So what just happened when we cloned? Well, Git pulled all of the objects associated with our project, including commits, file diffs, and tags. That's what those 49,241 objects that were pulled from the server on GitHub were. Once they were pulled in, Git compresses them into a single pack file. How big is that compressed file? We can use the du Unix command to get the size of the file in a human-friendly format. It's about 17 megabytes. Those 17 megabytes contain every commit, the files associated with that commit, and every tag on this project. To decompress the packed file, we can use the git unpack objects command. In the interest of time, I won't be showing a sample of this command, but feel free to put a pin on this note and play around with unpacking pack files later. So when we clone our code base, we bring along every object that represents the history of that code base. The packed object tells the story of years of commits, releases, and file changes. Now that we know what happens when we clone a repository, let's move on to the next phase of our Git workflow. Let's say that we wanted to make a change to the README within a directory. Typically, these changes will be isolated in a separate branch. We create this new branch by running the git checkout command. Standard output says that we switched to a new branch, but what actually happened under the hood? To answer this, we'll need to look inside the .git directory again. In particular, let's take a look at the contents of the head file. If you're familiar with Git, you've probably executed a command like git push origin head to push your updates to a centralized server. The contents of the file point to another file in the .git directory, located within the refs folder. Since we can explore everything in the .git directory, let's see what's contained within this refs file. It appears that the file contains a SHA-1 hash. If you're unfamiliar, SHA-1 hashes are used to uniquely identify commits in Git. I wonder if there's a way to figure out what the SHA-1 hash points to. As it turns out, there is. There's a useful command, git cat file, that allows us to print the details of an object that is referenced by a SHA-1 hash. Let's run it now and see. It turns out that the hash is a reference to a tree object. In this case, the tree object is a reference to a set of changes under a commit. If you've ever heard the phrase, a branch is a pointer to a commit, this is a literal representation of what that means. From this pointer, we can start to build a new chain of changes that is separate from the changes that exist on any other branch. Now that we've got a fresh branch to work on, we're going to make a change, stage it, and commit it. You might have heard those words used in context of Git before. What do they mean? Let's imagine that we've made a small modification to the README markdown file in this repository. We staged this change by running the git add command. The git add command essentially says, add this file to the next commit that we're making. Speaking of commits, we need to commit our change now that we've made one. To commit changes, we use the git commit command. Before we commit, though, we'll inspect the contents of the .git directory using the tree Unix command. We'll run tree before and after the operation to figure out what changed in the .git directory so that we can track down what a git commit actually does. I'll avoid pasting the full output of the tree here and just show you the difference. That is, the new files that were added after the commit was made. You might have noticed in the directory structure above that the first two characters in the SHA-1 hash are used as the name of the directory that the blob object is stored in. It seems like a strange thing to do, but there are several reasons that this is done. There's an operating system defined limit on the number of files that can be stored in a single directory. For example, if you're using a Mac OS system, you can only have 2.1 billion items within a single folder. This seems like plenty of space, but older operating systems have greater restrictions on the number of files you can store. Not to mention, some Git repositories can grow rather large, and you might very well reach 2.1 billion objects within a Git-managed repository. Second, operating systems generally execute a linear scan of the file system when looking for files. This search is done on a per-directory basis. By breaking up the thousands of objects that exist in an average Git repository into several folders, Git reduces the bottleneck associated with searching for these files and loading them into memory. So, there's 3 new objects that we've created here. For brevity, I'll refer to them as EC, DC, and 26 in the next few slides, by the first 2 characters within the SHA-1 hash. Let's take a look at the EC object by using the git cat file command again. It looks like the object represents the git commit that we just made. Like other commit objects, it contains the commit message, the committer, and the timestamp. Interestingly enough, I feel like I've seen the SHA-1 hash listed under the tree property. In fact, it's one of the new objects that were created after we made our commit. If we inspect the contents of this, we can verify that it is indeed a tree object. So what just happened here? Well, first, we staged our change to the README file. This created a blob object for that instance of the file. Then we created a commit. This commit referenced our latest README blob object and the most recent blob and tree objects available for other items in our repository. Speaking of that blob object, here it is. It was hiding in the object uniquely identified by the DC SHA-1 hash. I've truncated it above, but the new object contains the entirety of the contents of our README file. So, in summary, at least 3 objects are created whenever we make a commit. A commit object, a tree object, and a set of blob objects for each file that was changed. Now that we've got our modification made and committed, it's time to share it with the world. To do so, we'll push our changes using the aptly named git push command to a remote Git repository hosted by GitHub. What did this just do? Well, a couple of things happened. Our Git client sends any new objects created between the time of the last push to a remote Git instance. But there's also this business about compressing and counting all over again. What's going on here? Well, it turns out that here, Git has compressed some of the objects that were loose in our directory into a pack file, similar to the one that we saw earlier. How does the compression of objects to pack files work? Well, Git starts by sorting objects by type, then name, then size. Then it computes the deltas between adjacent objects. Sorting by size exploits a principle known as Linus's law, which states that file sizes grow with time. In this sense, by sorting the objects by size, you're implicitly sorting them by the order in which they were most recently modified. Once the objects are compressed, the index file, that's the one with the IDX extension that we saw earlier, serves as a table of contents, pointing from an object hash to its location within the compressed pack file. Why does Git generate a pack file when we do this push? It's likely that at the time we pushed our changes, there were multiple unneeded loose objects in our objects directory. For example, if you add and commit a file, then add and commit it again, you have two blob objects of the same file with a potentially small difference. Before pushing those changes to the server, it helps to compress them into a single pack file. And with that, our changes have been pushed to a repository on another machine. Now, you might find yourself in a situation where changes have been made to a file that you're editing by another person. In this case, you need to bring those changes into your file. This is commonly known as resolving a merge conflict. There are two ways to do this in Git, through a rebase or a merge. So what's the difference between a rebase and a merge? Let's start by talking about how a merge works. Let's try to merge the changes that we made in the development branch onto our master branch. Since there were no changes made in the master that did not exist in our feature branch, Git did a fast-forward merge, or it simply moved the pointer at the head of the master branch to match the pointer at the head of our feature branch. But what happens if there are changes in our master branch that don't exist in our feature branch? Let's try to simulate this by creating a new branch, staging and committing a change on master, then staging and committing a change on our new branch and attempting to merge. There's a lot going on here, but the most important thing to pay attention to is the output of the last command. You'll notice that, unlike last time, Git used the recursive strategy in order to bring our changes from the development branch into master. What does this mean? Well, for one, it means that a merge commit was created for our change. We can see that in the Git log right here. And if we print out the contents of the commit object associated with this commit, we'll notice something very interesting. The merge commit has two parents. All of the commit objects we've inspected so far have only had one parent. What are the parents of this merge commit? If we inspect them, we'll notice that one commit is the added test file commit that we added to the master branch. The other commit with the message added other test file was added to the development branch. You'll notice that both of these commits have the same parent commit. That's where the term merge comes in. The two branches split off at the point where the development branch is checked out. That's why they share the same parent commit. Later, they rejoined when the merge happened. Because the merge commit has two parents, we maintain the history of each branch that was merged. Now, let's cover how rebasing works. We'll start by doing the same thing we did in our last example, creating a new development branch, then making distinct changes to the development branch and master, then reconciling the changes using the git rebase command. Let's explore how the git objects were changed by this operation. If we take a look at the first two commits in our master branch, we'll see the following. We have two distinct commits. Using the handy-dandy catfile command, we can see that the commits have a parent-child relationship. So essentially, when we rebased, we created and interleaved the commits together to ensure that they had the proper linear hierarchy. When we merged, we created a single commit that joined two parent commits. And that summarizes the differences between a rebase and a merge. When we merge, we keep an explicit reference to the two branches that we merged at the expense of losing our linear history. On the other hand, rebasing allows us to maintain a linear history, but lose the explicit reference to our two branches. And that's the lowdown on Git. We've used nothing but our command line and intuition to understand what happens when we clone, make modifications, and resolve merge conflicts in a Git repository. To rehash what we covered, we talked about how Git represents key information as objects stored in the file system, how Git compresses loose objects into pack files to increase space efficiency, especially for large repositories, and what happens under the hood when we rebase and merge and the trade-offs of each approach. If this talk has got you fired up, there's plenty more resources for you. The Pro Git book is freely available online and a great way to get started with Git. It provides tons of technical details and is best consumed in bite-sized portions. The second presentation on Git pack files by William Shepard is a great way to learn more about pack files and how they're created. And finally, you can check out a collection of deep dives into the Git code base that I've written on my blog. Thank you for taking the time to attend this talk.